Hi, my name is Talia. I'm a staff member at Discovery, and I'm going to help you do your homework today. So this question is a little bit weird because there's two different variables that you have to deal with, and it's a little hard to distinguish which one is which and which one you have to use, and it's just kind of hard to read. So I'm going to start out just by explaining the two different variables and how they come to play, how they both come into play when you're figuring out how to solve this problem. So first of all, you're given some information about a study that was done to calculate the amount of sugar intake every American has daily. So it's just like one big study that was done, and you learned that it had a normal distribution. The sugar intake had a normal distribution, and we're going to represent that variable as x. So x is the sugar intake. And in that study, you learned that the average is 64 grams, and the standard deviation is 8 grams. So you can take this information as the true average of all sugar intake of all Americans, because we can assume that this study represents all Americans. The true average is 64 grams and the standard deviation is 8 grams. So, as you know from class, a normal distribution follows a bell curve like this. And this can be really, really helpful for calculating probabilities and calculating ranges and stuff like that. So the way we format a normal distribution is a little swiggle, and then n, and then you write the mean and the standard deviation. So the mean is 64, and the standard deviation is 8. So we know in a normal distribution, the mean is in the middle. So that's 64 grams, and then this standard deviation kind of just describes like how far things lie from the average of 64. So that's the first step. This study was done, and we learned that in America, because we can assume this study represents the entire population, we can assume that in America, the average sugar intake is 64 grams and the standard deviation of that is 8 grams. So that's over, that study's done. Now, you kind of want to test this out. So you take a sample of 9 people out of America, and you calculate their average sugar intake every day, their average daily sugar intake. And this average, this is your new variable here. And we learned from the central limit theorem that if you take a bunch of samples, the same size, and take the means of all those samples, those means follow a normal distribution. And this is a little bit confusing because this mean, this x bar, is variable. It's not always going to be 64 because, you can take 9 people and the average could be 61. You take 9 people, the average could be 70. But the one big thing is that it's going to cluster around the true mean. So out of these 9 people, you're going to calculate a bunch of means. And as we know from the central limit theorem, all these means follow a normal distribution. So let's construct that normal distribution, and we can do that using the information from the true population that we found that they found in the study. And that's why this is important, because without this, we can't construct a distribution for our own sample. And so the mean is always going to be the same. The mean is 64. And that's because it's most likely that your average is going to be 64. And that's right in the middle here. Because this is the true mean, all the other means from your sample are going to cluster around 64. And then the standard deviation, that's a little bit different. We call it the standard error in this case because it's affected by our sample size. And if you remember from class, our standard error in this case is given by the standard deviation of the population divided by the square root of n. And this makes sense because the more people you have in your population, the smaller your standard error is going to be. Because, if you have a lot of people, you take the average of all those people's sugar intakes, it's more likely going to be accurate to 64, so it's going to be spread less. But here, we actually have a pretty small sample size. Our sample size is only 9. So this is really going to affect our standard error. So in this case, to finish constructing the distribution, we have our standard deviation, which is 8, divided by the square root of 9, which is our sample size. So that's 8/3. So now we have these two distributions, and we have all our information about them, so we can go ahead and start actually solving the problem. And our problem is, what's the probability that, given our sample mean from our sample of 9 people, that mean falls between 61 and 66 grams per day? And I think I mentioned this earlier. A really good thing about normal distribution is that it makes it really easy to calculate probabilities like this, especially in a range. So pictorially, this is what that looks like. So we have our mean here, like our mean of the means is 64, and our probability that is between 66 and 61. Let's say 61 is like, 66 is right here-ish, and then 61 is like right here-ish. So the probability that our x bar is between 61 and 66 is this area in here. It's this little range of area. And we have some tools to use that. We have some tools to find that. We have Python functions and stuff like that, but we can't use them until we take one step that really simplifies it a lot and makes it a lot easier to work with this. And that's called standardizing the normal curve and finding your z-score for these values. And so a z-score is a value that represents how many standard deviations a value is away from the mean. And that sounds a little confusing at first, but let's show how that works out on a new normal curve. So with z-scores, our goal is to more easily calculate the probability and kind of like convert this to a simplified version of the normal curve. So let's convert it. And a standard normal curve always has a mean of 0. That's the big quality of it. A mean of 0 and a standard deviation of 1. So it kind of is broken up like 1, 2, 1, 2, like that. So let's standardize this normal curve and convert it over to this where the mean is 0. And we want to do that by changing these values into their z-scores. So we're going to have a different range for our probability, and our formula for finding the z-score of any value on a normal curve is the value minus the average over the standard error. So in this case, we have, for these two values, the probability that z, because we changed this x bar into a z when we standardized to follow this, is between 61, our value, minus the average of 64, divided by 8 over square root of 9. And then this is 66 minus 64 divided by the standard error, 8 over square root of 9. So let's calculate those. This becomes, and I'll write it down here so I don't go too far. The probability that z is between negative 1.125, which is less than 0.75. So on the new standard normal curve, we can kind of redraw where these values are. So 0.75 is like here, and negative 1.125 is like, that's not perfect, but whatever. And just kind of to reiterate, what these values represent are how many standard deviations these original values are from the average of 64. So for example, 66 is 0.75 times the standard deviation away from the average. And this is really how we start to calculate our probabilities. So we learned in class that there's two Python functions that we use to calculate the probability of certain z-scores. And that's norm.cdf, the cumulative distribution function. I'm pretty sure is what it stands for. And how that works is if we do like norm.cdf of, like, say this is like 1.5 z-score, we do norm.cdf of 1.5. That calculates the area from this z-score down to like negative infinity. It's all this area, because the area under this curve is the probability. But it might not be super clear at first how we're going to use that to calculate this range in the middle here, because the norm.cdf function, like, we don't want this whole area that goes from 0.75 onwards, because this little tail right here is not included in our little range. So let's just start out like showing what norm.cdf of 0.75 is. So we have this norm.cdf of 0.75. That's all this area here, kind of like I said, all the way down to negative infinity. Oh, my marker's kind of dying. But let's think about it. What's norm.cdf of negative 1.125? that's this area here. We scratch it out. Goes down to negative infinity. And if you look at the area in between there, like what's left, like this minus this is this range in the middle, if that makes sense. So you have all this area here and all this area here, and this kind of cuts out the extra tail that you don't want. And what you're left in the middle is the range that you're trying to find, the probability that you're within 0.75 and negative 1.125 or standard deviations from the average. So the trick here is kind of simple. You just subtract norm.cdf of the lower z-score. And if you type that in Python, which I did earlier, it's 0.643. And just kind of to reiterate what this number actually means, that means that if you're taking a sample size of 9 people and calculating their average daily sugar intake, there's a 64.3% chance that that average is going to be between 61 and 66 grams. And that's this area here. And that's also this area here. It's just easier to calculate it with our standard normal curve. So yeah, this area here should represent 64.3% of the entire area under the normal curve. So did you fall within the 64.3%?